Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode we're going to take a look at ion propulsion. So let's dive right into it. Now before we understand ion propulsion, we have to understand the physics of it. Now physics in this scenario is very simple. It's nothing fancy, nothing complicated. We have Sir Isaac Newton to thank for that, and all you have to understand is action equals reaction. That's it. There is nothing fancy about it. So either you throw a lot or you throw very fast, whatever you are throwing. Now in this scenario, throwing, like how you see this rocket engine and Saturn V and this diagram, what you are throwing is molecules. Now those molecules you can store either in liquid form like kerosene and liquid oxygen, and then you burn it and then you throw it down in gas form, or you can do ions. So at the end of the day, is basically you are doing two things that you are throwing out. You are trying to throw them out as fast as you can, because if you use hydrogen as it used in for its upper stage, you will get a lot of velocity. But if you used heavier element that you are throwing, and you throw a lot of them like a boost stage, you'll get a lot of thrust. So these are the two component of it. You throw a lot and you throw it as fast as you can. So this is the physics aspect of it. That's all you have to understand. Now, so if we want to understand ion propulsion now, or ion thrusters, all you have to understand is every rocket that we have that is big, that gets things off the ground, is generally relying on what we call oxidation, basically burning the fuel. Now fuel could be anything. It could be RP1, basically kerosene, it could be methane, or it could be a liquid hydrogen, or it could be nitrous oxide also. So all things combined, all we are doing is just taking a fuel, mixing it with oxygen, and that's reaction is called oxidation, and using that we are releasing chemical energy. Using that we are getting our thrust. Now that is common in every rocket, be it solid booster, be it liquid booster, or be it hybrid. However, in ion thrusters, we are replacing that oxidation stage itself and replacing it with ionization. Now ionization is a kind of different thing. All you have to understand, if you are stripping electrons away from a element, or basically a gas or whatever have you, you put like you create a scenario where you have basically charged particles. That charged particles is what we call ions. Now ions have the benefit that you can control it with magnetism or electricity itself. Like basically you have anode or cathode, ions will flow. So using these two principles, that you can use magnets to propel it, or the fact you can simply have two diodes, I'm saying basically two conducting material. So basically one is throwing the positive item, another is absorbing the negative item. You can easily get the propulsion item. So in this scenario, the same way the normal rockets are dual propellant system, basically you have oxygen and fuel. Here also it's a dual system. Basically you need electricity to do that ionization, acceleration using magnets, or creating basically what we call electrical field. You need electricity for that, but electricity itself will not gonna get do anything. You need fuel for that. Now in this scenario, fuel could be any gas that easily ionizes. So it's not a single component. So it still suffers from the same fact that you need two things. You can't just run it on one. You cannot be like, okay, I have millions of solar panels and tada, I have thrust. It will not work. You need fuel. And if you have just the fuel, it will not work unless you have the energy to ionize it. Now on top of that, this is the simple aspect of it. Using electricity, it gives very, very, very high specific impulse. Now all you have to comprehend about a specific impulse is that is the mileage of a rocket. That's it. Now be mindful that only describes the mileage, it does not describe the horsepower of it. So if somebody says that this rocket can go very far, you simply ask them what is the specific impulse. Now specific impulse will tell you how big the fuel tank has to be. Fuel tank in this scenario is basically oxygen plus the whatever fuel they are carrying. So if specific impulse is low, like for boosters, it's generally it's like a very inefficient, but we use that inefficient engine because it gives a lot of thrust. Basically it's like high horsepower cars are generally less fuel efficient compared to a low one. So it's as simple as that. So generally we measure specific impulse in second, and if you want to give a context to that, is generally below 500 second is what you can get or expect from a combustion engine, basically where you are combining liquid hydrogen and liquid oxygen. That's the best you can do, and no practical engine even reaches that point. So 500 seconds of specific impulse is considered awesome in chemical engines. So some engines can push a little bit here and there, but that's the upper limit. However, in this puppies, you can easily start off from 1500 and go upwards to 10,000. So be mindful, if mileage is a criteria, these puppies are the granddaddy of it. But because it has ludicrously high specific impulse, it also pays the price. The price being the thrust out of these puppies are minuscule. The basically, if you are familiar with rockets, you must say, everybody is saying, it has 500 kilonewton, it has 1 meganewton, and like big newton words. These are micronewtons of thrust. Basically, if somebody can build a ion propulsion that can give you 1 newton of thrust, it would be probably consuming hundreds of kilowatt of electrical energy. So be mindful, it is very weak. The thrust out of it's very weak. That's why you don't see rockets that have battery and this fuel. It simply does not provide enough thrust. It cannot get off the ground. So what are the pros of it? Why the heck, if it can't get you off the ground, why the hell we are even talking about it? Well, what do you do when you are in space? You can fire these engines, and because it has very low fuel requirement, I'm talking, let's say you want to get equivalent delta V, as in change in velocity, as in kilometer per second, that you want to add to your craft. If you try to do that with chemical fuel, be it peroxide fuels or be it simple liquid hydrogen and oxygen, you're gonna spend tons of fuel to do that. However, if you have a solar panel or nuclear reactor or RTGs to provide you with electricity, you can do that same velocity change. Like let's say you want to add 10 kilometer per second on top of whatever you got from your rocket. You can do that with few kilos of propellant, because this is so efficient. That is crucial. So let's say you are building a satellite which has giant solar panels, so electricity you are getting from sun, that's out of the question. The final mass. But using how much fuel you need very little. Like satellites that use ion propulsion for station keeping, basically they make sure the orbit remains perfectly balanced. They spend very little amount of propellant, basically 1 or 2 kilos, not 10 liters or 50 liters of hydrogen they need to have for station keeping. And it has very long endurance. Now that simply because I already said it has very low thrust, you have to keep it running for very long time. So think of it this way: if you are firing rocket right now, rocket will go forward. But if you fire an ion engine, it will start slowly. Now, if you are going to the moon, don't even consider about ion engine. Now, if you're going to Mars, now the rocket engine is going to start very fast. It's like, let's say, I'm talking from orbit, not from Earth. So you both have same orbital velocity. Now, all the chemical engine is going to be like, it's going to get very low. Now, if you start the ion engine, at first 1 week, you will have very slow speed. At second week, you have bit more. At third week, you're still more. At 1 month, now you are matching the speed that a chemical engine have. At 2 months, you are still accelerating. At 3 months, you are still accelerating. So the longer the duration of your acceleration, you can reach very high speed. So imagine it this way: your rocket is like a quick boost. It's like whoosh, done. This ion engine is like continuously working. Now, how far you can go? You can go very far if you have the energy, as in the electrical energy needed for this system. You can go very far, and you can go very fast. Like, let's say chemical engine will take 5 million years to go to Alpha Centauri. This can do it in very reasonable amount of time, which we call 50,000 years. So yeah, it is very fast. The longer the distance, the more practical these becomes, because they have very long endurance. The engines can keep running for continuously for months to years. It's not like you have rocket engines where you have to maintain for the cooling system and all that other things. The endurance on these puppies are very phenomenal, and it's very controlled and gentle. Because there is no explosion, it's very controlled. Like in these satellites, you don't need gimbals, fancy gimbals, and way to contain the explosion. It's very gentle. Now gentle, and the fact that it's very controlled, as in the thrust output is also very controlled. Well, let's say you only need minuscule of thrust, and I'm talking minuscule from its perspective. You can do that. Like, in many of who have been following SpaceX, is like they say like throttling a rocket engine is very difficult. It's very tough. You cannot go from 0% throttle to 100% throttle reliably. Like, you can generally have a operational range where you 100 to 70% is the throttle. They can go it very down, but they cannot go very low. But in these puppy, you can go like 1% throttle, 15% throttle, 100% throttle. Like, this whole aspect of controllability really allows you to keep station keeping properly. and it has almost no moving part aside from the fact that you have an injector that is injecting the fuel. Inherently itself, it does not have turbo pumps, it does not have cooling fluid running around it to basically liquid hydrogen or oxygen running around to cool the chamber. It's very simple, it has almost no moving parts inherently. So now the reason why I'm not going to give you a breakdown of ion engines, because there are hundreds of it. So this is a very rough idea. Is basically you put electron gun, basically what you used to have in your old TV, CRT TV, and it's giving you xenon, and using that you are creating a basically charged scenario here. Using magnets you are accelerating them, and to help things along you have a grid here which is negative grid. You have firing electrons, you have negative grid to absorb it, but you also have another neutralizing aspect, because if you don't neutralize it, even though you are getting acceleration here, the positive particles that are leaving, they will come back. So you will get very little efficiency. So for that reason, to make sure they don't come back, they don't interact with this grid, you also need what we call neutralizing electron agents. So it's very simple. Inherently it's very simple. It's just a basically it's more or less CRT TVs. So what are the consequences of it? The first and the most obvious one is very weak. And then when I say weak, I don't even mean it like okay, let's say it's weak enough that it can't get you off the ground, but in space also it's very weak. Like if you want to dodge let's say a debris coming to your satellite and you want to dodge it, you can't dodge using this. You need peroxide fuels for dodging maneuvers. You can't do quick maneuvers using this. It's very weak even in space. Now the fact that even though you need very little amount of fuel, you need insane amount of power to get even a reasonable amount of thrust. Now efficiency wise, if you are talking about a kilowatt to thrust, it's very efficient. It's like on orders and magnitude more efficient than rocket engines. You can achieve 50 to 80% efficiency from electrical energy to propulsion energy. However, you still need power, and when I mean power limited, think of it this way: the solar panels that you put on your spacecraft, while it's launched from Earth, it will have a lot of power because it's closer to sun. Now while it's going to Mars, it will lose power, and consequently your rocket engine will also lose power because ions need electricity to work. So for this reason they are very power limited. So all the Dawn mission and Deep Horizon missions that use ion engines, they are generally in very elliptical orbit. Sometimes they only use this when they are facing the sun, and not to mention that you can't expect these to go to Pluto. You can't reliably use these to go to Pluto, and that's why Pluto has everything we send to Pluto generally has RTGs. Now the fuel in itself is xenon. Now you might be like, okay, xenon is not that expensive. It is present in your basically flashlights and I'm saying flat lamps and commercial light applications. That's true, but when you're talking about kilos of it, and when you're talking about the tons and tons that you will need for human mission, the cost starts to pile up. And this xenon is very pure. The quality of xenon used for space mission, let's just say it's very, very, very expensive. And when you're talking about 1 or 2 kilos, it's manageable. But when you need tons and tons of it, now of course you don't need 500 tons. You may only need for 2 to 3 tons. But still, it's 2-3 tons of very, very expensive thing. Now there has been some research into making some things that use simpler thing like argons, which is very abundant, so it's quite cheap. But right now we generally use xenon. So these are the consequences: the serious fact that is power limited, secondary fact that is very weak even in space, and the fact the fuel right now costs. Now this can be solved if you have enough money. So what we can expect in the future? Now the biggest problem with this ion engine is power. Now how can we solve power? It's basically compact and light nuclear fusion reactors all we need. Now I will provide the link down below where you can see NASA's Kilo Power. Basically it's a nuclear reactor which is very light, very small, and can provide upwards of 10 kilowatts of electrical energy. The benefit of that is that if you put it in in your spacecraft, you can send it as far as you can, as long as this is working. And because the acceleration builds up over time, you can, let's say you launch it today, the rocket will leave it in behind in first few minutes. Now in months time this will start to catch up. In a year time it will exceed. In 2-3 years it will be so far, so fast, like you can literally try to catch up with Voyager, basically that is traveling at upwards of 19 kilometers a second. You can do those kind of acceleration. So if you're sending very far using nuclear reactors, you can reach Pluto in instead of 10-year mission, you can do Pluto in, let's say, 6 or 3 years if you have powerful things. So We need power. That's the biggest limitation. Second, the engines right now that are in use, they are very small. They are like 10 kilowatts, 50 kilowatts. We need megawatt scale to really push human scale ships. For this reason, there are some attempts to make very big engines, and there has been some recent attempts to go in a different direction. Ion engines is one type of electrical engines. There is another one which we call plasma engines. I will make another video on that. So basically, ion engines right now is very size limited. Now, to push something really big, you really need something big and powerful, because even though acceleration will be gained over time, your components will break down. Like let's say even this engine, it can run continuously, but does not mean it can run continuously for 100 years. So we have to make sure that it gives out enough power that time window for a useful extraction shrinks. So this was my presentation on ion engines. I hope you liked it or learned from it. In that case, please leave a like. If you didn't, don't worry about it. You can dislike it. I would urge you to leave a comment on my videos, and I would ask you to please subscribe, share it amongst your friends, and press the bell icon if you're free. And as always, thanks for watching.